Good day, everyone. Welcome to Gaia STEM lecture series of Taiwan Top Science Student Project. I'm today's host, Juling Shih from National Central University, Taiwan. I'd like to introduce our speaker today, Professor Betina Ip. She's a Royal Science Dorothy Hodgkin Research Fellow and Hugh Prize Fellow in Neuroscience, Jesus College, University of Oxford. Dr. Ip is a vision scientist and widely interested in anything that relates to sensory processing and the brain. Her research interests are in binocular vision, neuroplasticity, and neurochemistry. Dr. Ip graduated from University College London with a master in neuroscience. She then obtained a doctorate degree at Oxford, during which she focused on attentional modulation on binocular vision using non-invasive MR imaging. During her postdoc training, she made contributions to understanding how functional paradigms and neurochemistry via MR spectroscopy measurements can be exploited to study visual perception. In 2020, Dr. Ip was awarded a Royal Science Dorothy Hodgkin Research Fellowship to establish her own research program at the Wellcome Center for Integrative Neuroimaging as part of the Nuffield Department of Clinical Neurosciences. Her research focuses on investigating plasticity in human binocular vision system in health and disease. Without further ado, I'd like to welcome Dr. Ip to tell us, what does chemistry have to do with my binocular vision? Dr. Ip.
Thank you, Professor Shih. That was a very kind introduction. I just want to check first that you can hear me clearly. You can?
Yes.
Oh, that's wonderful. So I have been looking forward to speaking at this lecture series for a long time. It's a great honor to be invited to speak to you today. I think it's a really fun and important thing to talk about research with people who are usually not exposed to it. So thank you very much for organizing this. What I'm going to talk to you about today is something very, very close to my heart. It's about the relationship between chemistry and the binocular brain, hence the title. And the way that I have designed the lecture is, in the first half, I'm going to talk about binocular vision, to introduce this amazing ability of ours. And in the second part, I'm going to talk more about the brain. And in the final part, I'll talk a little bit about my career and how I've come to the place where I am today. So if you have any questions, or if there's something I'm saying that is not clear and you're just getting confused, I encourage you to write in the call messages, because I can actually see them and I would be happy to answer them while I'm going on with my lecture. So let's start with, let's see, slide forward. A regular day. You're waking up and it's a regular weekday and you're making yourself a nice cup of tea in the kitchen, pouring the tea into your cup, right? What's happening next? You're maybe working somewhere else, and you're taking the metro to go to work, and you're walking onto the escalator, and you're kind of moving through space. It's all very, very routine. At work, you are holding your phone in your hand, and you're talking to a colleague. There's somebody bumping into you, and your expensive iPhone is shaken out of your hand, and before it just drops on the floor, you catch it. And you go back home, and to relax from your workday, you play a bit of tennis with your colleague from work who has become very good recently. So all of these things that I have just told you about remarkably involve your binocular vision. And today I have 3 parts that I'm going to cover. So they all have a question involved. So part 1 is about what is special about binocular vision. Part 2 is the question, are babies born with binocular vision? Part 3 is about what does chemistry have to do with my binocular vision? And then I'm going to talk about careers. So what broadly is binocular vision? Let me just read out this definition from a book. So binocular vision is the coordination and integration of what is received from the two eyes separately into a single binocular percept. Now, I would say this is a pretty long sentence, and it involves a lot of actions. And to understand exactly what's going on, we really have to unpack the sentence and see what it means. Okay, so let's do this. And I have taken the liberty to look outside of the human visual system to give some examples of what binocular vision is. So let's start with the nocturnal tarsier. Let's look at its face and think about what are the most remarkable features that we observe. Some of you might think, oh, this one looks a bit like a science fiction character. Others of you might think, oh, these are remarkable big eyes that this animal has, and they are very, very large in respect to its body. So what I'm noticing is that the eyes are at the front of the head. And in fact, if we look at its profile, we can see that, the eyes are pointing forwards, and on the side, you just have a blind spot, pretty much like humans. Now, this is one extreme example of where eyes are placed in the head. Another extreme example is the common rabbit. Now, when we look at the rabbit from the front, you can see that, the rabbit can see us and we can see the rabbit. However, if we look at its side, imagine you're walking to the side of the rabbit. Oh, wow, the rabbit can still see us. There is no blind spot. It's looking straight at us. What this means is if you basically compare the visual field of these two types of animals, they both have two eyes, but they're remarkably different. So what we see on the left-hand side of our slide is the visual field of the rabbit, and in lavender is the monocular visual field, which means the part of the world that you can see with just one eye. And you can see that actually it covers almost 360 degrees with only a small part in the back that it can't see. Whereas the nocturnal tarsier has focused both eyes to the front, which means that it has a smaller monocular visual field, but a much expanded binocular visual field. And what I mean by binocular visual field is it's a place where both eyes can see the same thing. And if we look at different animals and how many degrees of the visual field they cover with both eyes, what you can see is that it varies actually widely. Okay, and the way that scientists have tried to explain this variation in visual field coverage, binocular visual field coverage, involves the idea of some animals really needing to see other animals as they approach. So maybe they're prey animals, like a rabbit, like a sheep, like a cow. And other animals are hunters. They like to hunt prey animals, and what they need to know is exactly locate where these animals are. Because what I'm going to talk about next is the actual advantage you get from having binocular vision. So first of all, I want to say that having two eyes is simply a better insurance. It's a better insurance because it can happen that through accident or disease, you lose one eye. And that's very common in the animal world because, animals, they interact with each other very forcefully. So in this example here, there's a picture of a lion I found online, which had an eye missing. And there was a paragraph explaining that despite this missing eye, it had just killed a wildebeest earlier in the day. So this animal was thriving, even though it had only one eye. So in summary, having two eyes is better insurance, and it just is a redundancy because if you lose one, you have the other one. So now about the actual advantages of binocular vision. When you do have it, what does it give you? So we know very well from many decades of vision science that having images presented in the binocular visual field allows you to see things sharper. So there's a 10 to 30% increase in the visual acuity if you compare binocular versus monocular vision. there's also a better ability to detect things. There's an increased ability for contrast sensitivity in binocular versus monocular vision. And what I mean by contrast is the difference between dark areas and bright areas in the image. So when you look at this cat and it's hovering on the ground looking at something in front of it, you can imagine how hard its binocular vision is working to see what's in front of it. So what could it be doing? Well, it's probably got something in front of it that it really wants to catch, right? That's what cats do. So another very, very important advantage of binocular vision is that it gives you extremely good distance perception. So when the cat is wading in the grass and it might be looking at a mouse, it's assessing where exactly is this mouse, so I can pounce on it. And in this picture, it has decided to pounce on it, but didn't quite catch it. So a little bit more about depth, because I think that's a really, really critical part of a critical function that binocular vision gives us. And I want to make sure that we're able to dissociate the types of depths that we see and understand exactly which type is associated with binocular vision and which type is actually independent of binocular vision. So who knows this better than painters, right? Painters have been recreating images of the world for centuries. Some of them are very realistic. And from the Western tradition of art, there's a clear drive to integrate depth cues into paintings. So I have included an example from the Dutch painter Johannes Vermeer. And some of you who like art and who have been thinking about art and vision might say, well, where are the depth cues here? So I'm going to point them out to you. So in the next slide, I have pointed out the different depth cues. Sorry, can you please leave? It doesn't matter. You can watch something. Sorry. The different depth cues that we have in this image are, for example, size. The lady in the back is small compared to the tablecloth here because she's in the back. There's occlusion. The chair is behind the tablecloth, so you can see that there's some part of it is covered. There's shading. The cembalo here has a very nice gradation that shows its shape. And there's, of course, spatial perspective with the lines disappearing to where the vanishing point is. So all of these cues, if you look at it with both eyes and one eye, they are really, really the same. And we call them monocular cues for depth. And there's another cue for depth. Before I go on to that, I wanted to also point out that these monocular cues can actually be played with in a way that they become visual illusions. So this is a very famous visual illusion called the Ames room. And you might be surprised that there are people of many different sizes, but such different sizes seems improbable. And what is basically happening here is that there is a very clever distortion in the way that perspective is used to make your brain think that this girl here is actually tiny and this girl here is gigantic. So if we break this down into a diagram, what we can see is that this person who is very, very small is actually, of course, far back, but you have painted the pattern on the floor and constructed the room in a way as if she was on the same level as the big girl. And you can only do this, and it's really only an illusion, if you look at this image through a peephole. Okay, so what I'd like to point out here is that there's a viewing peephole that is so small that you can only look through it with a single eye. Okay, so you might wonder, why should I not see it with both eyes? I will explain to you in a moment. Before that, I want to show you another illusion, which is called the spinning ballerina, because another very strong cue for depth is motion, and motion we can see with a single eye. Things that are close to us move very quickly, things that are far from us move very slowly, and that is something called motion parallax. Motion parallax itself is also ambiguous, which means that it can be seen at different depths, even though it's the same visual information. So I'm showing you here the spinning ballerina. And I encourage you to type into the message box which direction she's spinning in for you. So what do you see her spinning in? She's spinning with her legs to the left, or is she spinning to the right? Professor Shih is saying clockwise, clockwise. All right, so while you're looking at this, I'll just carry on. But I think some of you might be seeing her spinning anti-clockwise, and some of you might have experienced a flip in the direction that she's spinning in, which is basically showing that in this monocular image of depth that is using motion as a cue, there's no real information about the depth. It's still ambiguous to the degree where the spinning itself can be going left or right. So back to my point about stereo. So stereopsis, when I say stereopsis, it means seeing depth in the world with both our eyes. And if we think about the way that the eyes are placed in our heads, they're horizontally separated from each other at a specific distance. It's about 63 millimeters. What this means is that, very simply, if you close one eye and you look at the world, and you close the eye and look at the world with the other eye, you can see the image jumping around a bit, okay? This is something extremely basic, right? But what it means for the visual system is that it sees the world through two different perspectives that are very similar to each other, except in small systematic ways. And what I mean is that images that are at the point where your eyes are looking are actually creating a difference of 0 when you compare the retinal image from the left and the right eye. This is simply due to the fact that your eyes are looking at the same point. Yeah, so you compare the images on the back of your eye and you overlap them, there is a net difference of 0. This is called the fixation point. However, if there's an object behind that point, that will actually now create a difference in the images on the back of your eyes. We call that far cue, and it's also called uncrossed. It doesn't really matter. But what it means is that there is a systematic difference in the images that's given to both your eyes that's related to the fact that an object is away from where you're fixating. Now, the same can be said about an object that is closer to you from where you're fixating. That image, that object is going to create the opposite kind of difference on the back of your eye. So now this is quite interesting, right? There is a new cue that is being created simply by comparison of the monocular images. And it's this kind of cue that's a difference cue that is specific for stereopsis. So now I'd like to talk about history of science, really, which is 2 discoveries, scientific discoveries that led to the true study of stereopsis in visual neuroscience. And one is an instrument, which is invented by a British scientist, an inventor called Charles Wheatstone in the Victorian times. So Charles Wheatstone realized that if you present images to each eye separately, and there are these very small systematic differences between them, the person who's looking through his instrument, called a stereoscope, will actually perceive depth. Okay, so that's amazing because you are creating the 3rd dimension out of 2 dimensions simply by displaying something through an instrument. So what I'm showing here is the original stereoscope by Charles Wheatstone, which is in a museum in London. And back then they were interested in seeing, photography. photographs in depth, so that's why you see a landscape picture. And on the diagram, I have illustrated to you what exactly it does to the observer. So the observer would be sitting in front of the stereoscope. There's a mirrors attached to each side of the central pillar, and the pictures are on the side. So what it means is that your left eye is going to see one image, and the right eye will see another image, but what your brain perceives is a single image that's actually in depth. So using the Wheatstone stereoscope and manipulations of the systematic differences between the pictures that are shown to the left and the right eye, Wheatstone has demonstrated that there are ways to show near depth and far depth using the Wheatstone stereoscope. Okay, so that is one scientific discovery. And the other one, oh, sorry, before I go into that, I wanted to point out that in the animal world, what is stereopsis actually used for? So we're talking about binocular vision stereopsis, and what that translates to is really better ability to detect things, which means better hunting skills and better location skills. And that can be especially useful for animals who are what you call ambush predators, which means that they look at something, they assess its depth, and then pounce on it. Okay, so in the natural world, the way that we see things, every cue of depth is actually packaged up together, right? And they are consistent with each other. Monocular depth, binocular depth, they're always the same. But in science, I'm sorry, they're always on the same object, right? But in science, what we really want to do in order to study something in detail is we want to get rid of all the things that we're not interested in and focus only on the cue that is what we want to look at, which is stereopsis. So another scientific discovery which allowed us to do this is from the Hungarian vision scientist, inventor, and actually also artist, Bela Jules. So Bela Jules came up, he's also a computer scientist, so he came up with this idea of getting rid of all the monocular cues of depth and having an image which is only giving you tiny differences in the monocular cues, so that you come up with what is called the random dot stereogram. So if I was giving a lecture in person and all of you were in the lecture theater, I would give you these glasses, which are old school, but they work. And they basically, what they do is they give one image, one color to see, one eye, one color to see, and the other eye, the other color to see. So when your brain sees this, it can detect the differences between those two colors. So when I put these glasses on, I can see a square popping out. You will not be able to see this unless you have red-green glasses at home. But the point really is that what is happening in the stereogram is that there's no monocular cues for depth. There's no object to see. The only thing that's there is the tiny differences in the horizontal positions of the dots that define the stereogram. Okay. So now, with these two discoveries in place, the fact that we need to present two things separately to the eyes and the stereogram, we're actually really well equipped to look at stereo vision in all kinds of different species. And I've pulled out two examples which I found really fun that show the use of stereograms and presentation to two eyes to demonstrate that mantis ants and other animals can use stereo for prey detection. So this is a video of a mantis ant in its natural environment. And what it does is it has got these two pinchers, which are very powerful, and it's looking at its prey, a bee. And then what it does is it basically strikes out, right? Amazing how quickly it does that. So Nityananda and Jenny Reed have put red-green glasses on these mantis ants. And mantis ant is very happy doing that. And what it means is that the only cue for depth for this mantis ant right now, as it's wearing these glasses, is this stereopsis cue, okay? And because they want to check whether mantis ant uses depth for detecting its prey, what they're doing is they're changing the disparity, the difference between the two images, to see whether at a particular depth the mantis ant strikes out. And what it does is, yes, the moment at which it strikes is completely related to where the dot seems to be appearing to the mantis ant in depth. So when it's appearing in striking distance, about 7.5 centimeters from the mantis ant, it makes this strike. Okay, so that's a great demonstration of not only the methods, but also of the fact that mantis ants use stereopsis. Another example, recent example, is really cool, is in cuttlefish. Cuttlefish also have two eyes, and the experimenters were interested in whether cuttlefish use stereopsis, and again, they use red glowing glasses and random dot stereograms. So in this video, I'll skip forward to the moment where it gets, so mantis ant is in the tank and it's swimming around. Experimenter goes in, takes the cephalopod cuttlefish, and then gives its glasses. So here it's wearing these red green glasses. They're glued to the animal. And now it's seeing one view with one eye and another view to the other eye. And behind it appears the display screen, and there's a control. This is a control condition where the shrimp, its usual food, appears on the screen, and you can see it already kind of, oh, boom, it's reaching out with the tentacles to strike at it. And what they've done is they've basically tracked the distance of its eyes to the screen, which is flat, and see at which point it makes these very kind of stereotyped pounce maneuvers towards the shrimp. And what they found is that it's very, very reliable, that depending on the distance perceived by the cuttlefish, the pounce maneuvers is enacted at different types of distance from the screen. So when it's at the flat, at the distance of the screen, it has, say, 10 centimeters. If the shrimp is appearing to be farther away from the screen, it goes closer to the screen. When it's appearing closer to the cuttlefish, it kind of goes farther back. So that's a demonstration that cuttlefish lose stereopsis. All right, so enough about random dot stereograms and animals, non-primate. I'm going to give you only a single slide about this, even though it's been serious study in neuroscience for many decades, which is the representation of disparity, which is the difference between monocular images that is used to stereopsis, the representation of disparity in the primate brain. So what we know is that there are cells in the primate brain that are extremely sensitive to where objects appear in depth. And that means that the brain lights up when it sees things that are in binocular depth. And when we look at the distribution of sites that people have looked at for this kind of selectivity, okay, so let me explain here. What you have here is a stimulus which is displayed at fixation, and then it gets varied into near positions and far positions. What the neuron is doing, it's firing higher to the points that it likes best. So this neuron here likes fixation disparity best, and this neuron here is slightly displaced from the fixation disparity. So selectivity for disparity exists not only in the early areas for vision that are at the back of the brain, it's actually found throughout the visual cortex and also in regions that are multisensory. So what this means is that the cue for depth from two eyes is so important that neurons all through the brain really, really need it for doing what they usually do. And when we think in very broad terms about how the visual brain organizes information for different tasks, we bunch them into two pathways. One pathway, which is going from the back of the brain towards the front, which is called dorsal pathway, and one pathway which was going from the back of the brain towards the bottom front, which is called the ventral pathway. And these two pathways are basically doing what we think is spatial vision and object perception. So because we have neurons that are selective to disparity in both these pathways, we understand that disparity is used for both these very important tasks for the animal. But I'm not going to talk about this anymore, because I want to really summarize this part and answer this question. So what is so special about binocular vision? I've shown you in part 1 that it's ubiquitous, which means that it's common across species, but the amount of binocular overlaps varies a lot across them. It is also very powerful because binocular vision can break camouflage, allow you to detect animals that are hiding. It increases visual sensitivity and creates this amazing sense of solid depth. It is extremely precise and it's very specific. We can isolate it from all the other cues of depth. And it is computationally important because we know that there are populations of neurons across the cerebral cortex which actually like to see disparity. So that's part 1. And now we're going to move on to part 2, which is starting with the question, are babies born with binocular vision? And I encourage you to now, in the next 15 seconds, formulate an answer and type it really quickly in the call message. And I want to see what you think. Are babies born with binocular vision? What do you think? Tell me. Yes? No? 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 Okay. All right. There maybe, I think so. Wonderful. I love this variety of answers. And to be honest, when I started this research, I had no idea either. So the answer is binocular vision actually appears in the first months of life. And that appearance of binocular vision really depends on experience. And that's a really, really amazingly important idea. And it's been demonstrated. So a very convincing demonstration in babies is that babies usually start showing a very typified neural response to binocular stimuli, like random start stimulus, about 4 months from birth. So when you record their responses using a EEG cap, usually just looks like a hat that you wear, and you record the responses in the visual cortex. This kind of very specific response to binocular random dot stimuli that we now know about with stereo shows you one type of signal, but it appears at 4 months. Now you could ask, oh, well, this timeline could also be simply due to pre-programmed genetics. So imagine that baby is conceived, and 9 months afterwards, plus 4, is when this response appears, because basically it's hard wired, and it appears at 13 months always, right? So these researchers from Jando et al.'s lab, they looked at babies who were born premature, because if the response was pre-programmed, premature babies should have the same onset time of binocular vision as babies who were born at term. And what they found was that actually babies who were born premature had binocular vision responses 2 months earlier, which means that binocular vision is not pre-programmed. It actually depends on eye opening. So the moment that the infant opens his eyes, whether it's born at term or earlier, starts entraining the visual system to start receiving information that it uses to see in binocular depth. So, so that's one important thing. We're not born with binocular vision. The other really, really important thing is that, okay, we acquire binocular vision maybe in the first 4 months, but there is a longer period of time, which is called the sensitive period, where this ability can actually be interrupted. So this is now a little bit more serious. we're going to talk about a neurological condition that is known as amblyopia. Popularly, it's also known as lazy eye. It starts with the eyes, but actually has to do with the brain. So what you see on the left-hand side is an eye doctor who is testing a child to see whether she has amblyopia or not. And for doing that, she's looking at the visual acuity from one eye and compares it to the visual acuity of the other eye. And if you have amblyopia, the visual acuity between those two eyes will be different. One eye will be much better than the other. The factors that cause amblyopia are actually easily treatable. So they include misalignment. So if one eye is pointing in a slightly different direction from the other eye, that's fixating. That is a common cause for amblyopia. Another common cause for amblyopia is if one eye has a very different visual refraction. So it's giving your visual system a blurry image compared to the other eye, which is giving you a clear image. So in both cases, there is a mismatch in the information that the brain is receiving about where things are in space and how they look like. And this mismatch causes the brain to develop amblyopia. So it is the most common vision disorder in children across the world. And what I've shown you in this picture here is a map of all the areas that scientists have studied to look at the proportion of people who have amblyopia, and that varies usually between 1 to 5%. So 1 to 5% of the general population has this condition. Let's talk about what it looks like for a person who has amblyopia, what the world looks like. So a person who has amblyopia has one eye which is giving a very sharp image, which is what we call a good eye. Sometimes we call it fellow eye. But the fellow eye gives you sharp image, and you use it for all kinds of things, like walking around town, and you're detecting objects, you're making distance judgments, and you're reading, right, with your good eye. On the other hand, with the bad eye, which gives a blurry image, you cannot do these things very well. So because it gives a blurry image. Now, one reason why we want to treat amblyopia, of course, is because we want both eyes to work together. We want people to have binocular vision, and we want to have them see the world well with both eyes. Because what can happen in some cases is that due to accident or eye disease, the good eye deteriorates, and you're only left with your bad eye. And that leaves you reduced vision for a very long time. So there's good reasons why we need to think very hard and work very hard to treat amblyopia. Now, the good news is that there is a very easy treatment for amblyopia. Okay, so you all must have seen children wearing an eye patch in school because they are receiving a treatment for lazy eye. And this treatment usually takes 6 months, but it's incredibly effective. So children who are very mild amblyopic at the beginning, so they have very reduced vision on the poor eye, come out of therapy with a normal vision. So children are happy. They have an easy, cheap treatment for amblyopia. However, when do you ever see adults with an eye patch? That really doesn't happen for medical reasons other than surgery. Adults are not treated for amblyopia in the same way. And the common wisdom, the clinical wisdom, is that they're not treated because their brains will not learn to readjust the information anymore. So there actually is no treatment for adults with amblyopia. And when your amblyopia is detected at this age, so beyond the age of around, say, 9, you can be told, I'm sorry, there's nothing we can do about it. So that is very sad. However, now let's look at the counter evidence. There are some interesting studies, clinical studies, that have looked at the effect of damage to the good eye on visual acuity and the poor eye in amblyopes. And interestingly, what they have shown is that as the visual acuity in the good eye gets worse because of, in this case, age-related macular degeneration, what happens in these amblyopes with the bad eye that previously was ignored by the brain, it started getting better. Now, this is really interesting because it suggests one thing. It suggests many things, but one of the important things it's suggesting is that there's something going on in the interaction between the good eye and the bad eye, which is changing the visual acuity in a way that when the good eye is weakened, the bad eye suddenly starts perking up again, right? So there's something active going on in the dynamic between those two things. Doesn't seem to be completely fixed, which is amazing. And another line of evidence, which is very strong, started in this study, which is from Dennis Levi at Berkeley. And what he's looking at is the ability of adult amblyopes to improve vision in their bad eye with training. So what we mean by training in vision science is we do a task which is really, really simple over and over and over until we get better at it. So it's very repetitive. It involves lots and lots and lots of trials. And in this experiment, what they've done is they've asked amblyopes to train with their bad eye to detect the position of a line, and to say, for example, this bottom line is to the left or to the right of the top line. It's a very simple task. It's just comparable to visual acuity, right? Because you have to make a judgment between two separate elements. So what they've shown is that as amblyopes trained their bad eye over many, many days, their ability to detect the smallest difference in their position actually improved. And this is amazing because, well, clinical wisdom is that you can't improve vision in adult amblyopes anymore. It's too late. But this study really shows that it's possible with visual training to improve their ability to see these stimuli. So what has happened since then, that was in 96, is that there's a lot of very, very supporting studies coming out with different experimental paradigms that show exactly the same thing. So when you train the poor eye, you give it a task to do over many days, the ability to see with that eye improves. So basically, wow, now this is changing things. Instead of saying there is no change in the ability to see in adult amblyopes, what we now have is evidence, strong evidence that changes are possible, improvements are possible, even though the improvements are not on the order that we see in children. So I'm going to summarize this part, and I actually don't know how much time I have left. Do let me know if I run out of time. So in this part, we were starting with the question, are babies born with binocular vision? We all didn't know the answer properly, but scientists have shown that babies are not born with binocular vision. It is something that's critically dependent on experience in early childhood. And then I showed you that this experience critically then depends on normal experience, because if your binocular experience is not normal, you can end up with a condition called amblyopia, which affects the visual brain, and it causes decreases in visual acuity in the poor eye, including losses of binocular vision. And then we've seen that counter to common wisdom, amblyopia can improve in adults somewhat. Okay, so this moves on to part 3. What does chemistry have to do with my binocular brain? And I guess you wouldn't usually connect those two elements. So I just want to break this down a little bit. What's happening in amblyopia is it seems to be that one eye is very strong, so it's giving you sharp vision, your brain loves that eye, and one eye is really weak. And we've also seen that this kind of balance between the two eyes doesn't seem to be fixed in stone. It can be changed because of eye disease, or it can change because of visual training. So what is it in the brain that can change the balance from each eye? So let's look at how the visual brain is organized. In the middle, what we have is a diagram showing the input from each eye and as it arrives and how it arrives into the visual cortex. So what we notice is that input from each eye is actually separated all through the visual system until it reaches the primary visual cortex, which is the first site of processing in the cerebral cortex for visual information. So in other words, information from each eye arrives in separate bundles, and it's only in the primary visual cortex where these neurons connect up to other neurons that are taking binocular input. And why is this important? Because if you step away from that particular part of the visual brain, what you have is neurons that are already combining information from each eye. So ideally, when we're wanting to change the balance between each eye's input, it needs to happen at that stage where these things are separate, right? So a very kind of simple diagram of how this might work is shown on the right. We have separate info from the left and right eye, as I just explained. They arrive through excitatory neurons in the back of the brain where they're competing for input into a binocular neuron. Now, importantly, there are different types of neurons. There are neurons that are excitatory and there are neurons that are inhibitory. And excitatory neurons primarily pipe information to other neurons to say, hey, there's some kind of stuff happening here that's important to you. Please be excited as well. They send action potentials. However, inhibitory neurons, what they do is they modulate this information. They try to bring a bit more selectivity and into the kind of neural chatter by saying, oh, you should be quieter here, you should be louder here, you should be more attentive to this kind of information. So they're really kind of trying to modulate the excitation. So we're really trying to focus on the role of these neurons that are basically using chemical signals to communicate what is important to them and understanding how that relates to amblyopia. So when we look at the evidence that has accumulated over the past couple of decades on the role of excitation and inhibition, the main finding is that there seems to be a specific role for cortical inhibition. So the chemical called GABAergic inhibition, that makes neurons modulate their responses in amblyopia. So there's a lot of evidence from animal models, ranging from cats, mice to rats, that manipulating the action of GABA changes the ability of that animal to respond to stimuli with their weak eye. And that's in animals that were made amblyopic and animals that are at a mature stage, so adult animals. And this kind of body of evidence really generated a lot of excitement also in popular science, because it suggested that, amblyopia, the most common visual deficit in children, can be pharmacologically treated to restore vision. Now, of course, then scientists went on to study similar kinds of basically drugs in humans that can only be done for certain types of drugs like fluoxetine, which are already licensed for depression, for example. So when they tried to replicate the findings that they have made in animals in humans, the findings were really mixed. So this particular agent called fluoxetine did not enhance the visual functions of adults, humans with amblyopia, and other kinds of drugs also did not do anything. So donepezil or levodopa did not seem to have any effect on these adult amblyopes to improve their vision. Basically saying that these findings in animals are limited to these animals. And what we really need to do in humans is to understand what is going on with the brain chemistry in humans. And that is pretty much my field of research, because the only way really we can study the chemistry of the brain in alive humans is using what I call a photo booth for the brain. Other people know it as an MRI scanner, and to use the power of the MRI scanner to look at the brain chemistry. So what a brain scanner basically does is it maps protons in water and looks at the resonant signals of protons in your brain to dissociate different types of signals. And I'm saying this really broadly because we're able to look at anatomy, we're able to look at reconstruct white matter, gray matter, and cerebrospinal fluid in your brain using the signal. We can reconstruct high resolution anatomy. We can also look at changes in the hemodynamic, which is basically a correlate for neuroactivity in the brain to visual stimuli. So these are things that we do routinely in the MRI scanner. One thing which is fascinating, which is quite challenging, is actually to look at the chemistry of the brain. And why is this challenging? It's because the chemistry of the brain compared to the water signal is extremely small. So the brain is about 80% water, and that's what we're mapping usually with MRI. And if we look at the peak of water using spectroscopy signals, you can see that it's extremely clear and very, very high. Now, if we're interested in the chemicals in that part of the brain that we're kind of monitoring, here I've kind of put an example area in the visual part of the brain. If we want to look at the chemicals, we actually have to get rid of the water signal, suppress it completely, because the chemicals are at so low quantities. So let's suppress water. Water was where we have this little arrow now, it's gone, and we blow up the image by 3,000 times. And just there, very, very, very small but visible, are the chemicals. So what we're measuring here is the distortion in the resonance signal of water as a condition of it being embedded in different chemical structures. So depending on the structure of the chemical, the protons will be stretched either, they will be more or less detectable, which makes them shift on this axis called chemical shift axis. And the important thing to know is, like, chemists amongst you would know this very well, is that the position on the chemical shift axis tells you about the identity of the structure, and the height of the peak tells you about the concentration. So spectroscopy uses these principles in the human brain. And what we can see is that because we know the chemical structures of a lot of the neurochemicals, what we're able to say is with great confidence, at this particular position, there's GABA. At this position, there's glutamate. GABA and glutamate are measures of excitation and inhibition in the brain, can be measured with spectroscopy. Okay, so now I want to invite you to do a little exercise with me, and it's meant to establish which is your dominant eye. So what I want you to do is form a kind of aperture with both your hands, where you have a tiny kind of little bit left in the middle. You see this? Okay. And I want you to look through this aperture with both your eyes, yeah, until you center it on the red dot on the screen, okay? So now you have the red dot in the middle of this aperture. You're looking at it with both eyes, and now you slowly, slowly pull your hands closer to your face. All right, keep looking at that red dot, but just slowly pull your hands closer to your face. Pull closer and closer and closer and closer and closer and closer, 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 closer. Keep the red dot to the middle of your aperture, okay? I hope you've done that. Now, because at the point where your hands are very, very close to your face, you would only have circled one of your eyes. I want you to say to everybody else in the meeting, which of your eyes was the one that ended up seeing? Was it the left eye or the right eye? So I am going to tell you what I have, which is right. Okay. Left, right. Yeah, perfect. So what we will see is actually a distribution of answers between left and right. You have your eye dominance, and that seems to be a reliable trait if you do this exercise again tomorrow, it will probably end up being the same eye. Everybody has a little bit of an eye dominance. Okay, you may not have thought about this, but in vision science, we find this really, really interesting because it might give us a clue about what's going on in the visual system as we combine images, but also in the visual system of people who have this really dominant eye, like in amblyopia. So what I've done is I've basically quantified exactly how much eye dominance each person has in a study. These are people who have normal vision, they have normal binocular vision, they have sharp vision in both eyes, they don't have amblyopia. Okay. And they do this task called binocular rivalry, and I just simply quantify how much eye dominance they have. Everybody has a little bit of a different eye dominance. And then I measure the amount of GABA in their visual brain using an MRI scanner. And I ask myself, are these things related? Because if inhibition, cortical inhibition, plays a role in this mechanism that we think is involved in balancing the eyes, then there should be a relationship, right? And what we found was, yes, there is. In this small group of participants, there's a negative correlation between eye dominance and GABA in the visual brain, which basically means less GABA means more eye dominance. Okay, so of course, this was done in normally sighted people. We want to know about people who have amblyopia. How does that work out? So another group in Berkeley has actually asked this question. And they measured visual acuity in amblyopes who have good acuity in one eye and bad acuity in the other, looked at the difference in the visual acuity and correlated that to GABA in the early visual cortex. And again, as we see, less GABA means more eye dominance. Now, this is really fascinating. It suggests that the dominance of one eye is not due to that eye having more dominance, the strong eye, kind of forcing down the weak eye. It means that the weak eye may be just failing to inhibit the strong eye because it's a negative correlation. So in summary, I'm running out of time. These studies in humans using spectroscopy have shown that there is a role for GABA. It relates to eye dominance in normally sighted, and it seems to relate in visual acuity loss in amblyopes. And that this relationship seems to be going in the direction of the weak eye failing to inhibit the strong eye. And what we're doing in my lab next is to understand exactly how GABA, as a measure for plasticity, as a measure for eye dominance, relates to the ability of adult amblyopes to improve with training. And we're using virtual reality to ask this question. If you have questions about this, I can tell you later, but I think it's time for a general summary. So in this talk, I've provided you an overview about binocular vision, what it does, how amazing it is, and the fact that stereopsis is actually a cue that's created from the two eyes alone. We've also talked about the plasticity of the visual brain, that it's something that comes through experience, that because of this, we're actually vulnerable to abnormal experience, which causes amblyopia. We've talked about the ability to improve your amblyopia after childhood, and there's now evidence that is possible, and also that the chemistry of the brain is involved. And I have no more time, so I will probably stop here.
Thank you, Dr. Ip, for explaining the complex research with an easy to understand and very, very interesting way. Now I'd like to open up the floor for questions and discussions. And I believe our audience have many, many questions that follow up with your interesting talk. You can use raise hand button to talk to our speaker today, or write down your question in the chat box and we can relay your question to Dr. Ip. While we are waiting for questions, may I initiate the discussion with one question? I'm thinking about the amblyopia. When we treat amblyopia people, we ask them to wear the heavy glasses right now. We often see them wearing the heavy glasses. Do we actually strengthen or weaken the amblyopic eye?
So you mean children or adults?
Let's say children.
Mm-hmm. So many children who have amblyopia need to wear glasses. There is a relationship between the amount of blur they're experiencing and the depth of their amblyopia. I think that, sorry, I didn't quite understand your question. You're saying...
I'm thinking maybe I shouldn't say it's a treatment. It's just we are helping them to see more clear, right?
Mm-hmm.
So their vision will stay the same, is my question. Yeah, so it doesn't really strengthen or weaken their eye ability, their vision.
I see what you mean. Does the refraction itself change their ability to see with the weak eye?
Mm-hmm.
So if the amblyopia was detected after they have worn glasses, it doesn't make a difference. Mm-hmm. Because they would be wearing the type of correction that's appropriate for that eye after the treatment. It can happen that amblyopes don't want to wear prescription on their poor eye because it doesn't make them. They feel like it doesn't make there's no point because they don't feel like they're using that eye. In those cases, lack of visual correction can actually cause deeper amblyopia. So there is an interaction between visual refraction and the state of amblyopia that depends on glasses wear. Yeah.
Okay. I kind of see what it goes.
Yeah.
I think we have some questions in the chat box now. Let's start from the Guo. Would it be better if we have one more eye?
That is a great question. You mean 3 eyes? There are spiders who have 8 eyes, right? So I think to answer this question, I think we are already getting all the information we need to function as primates from having 2 eyes in a way that is obvious because we only have 2 eyes, right? So having 2 eyes allows us many evolutionary advantages for depth perception specifically. That's the ability to manipulate things that are really, really small and precise, That's something that primates do and others don't do so much. Having a 3rd eye, maybe in the middle of your forehead, doesn't really provide you with that much more information. So you might want to look up some of the literature on animal vision, which is really fascinating, looking at the advantages of having multiple eyes for arachnoids, for example, for spiders, and how they use their extra vision to do the things they do.
Interesting. Back to the amblyopic. 现在所知若是治疗的最大年纪的 oldest, the highest age for curing amblyopic.
So across, so the age at which people prescribe amblyopia therapy in standard care ranges, the upper limit ranges between 7 and 9. Yeah. And after that, it is debatable. It is being debated whether it makes any sense or not. So it is being debated if it makes sense for adolescents. There's some data showing that patching therapy, so covering the eye with a patch for many months, has an improvement for adolescents. But the amount of patching you have to do starts becoming quite excessive given the improvements that you get in that age range. So when we look at this period of plasticity, what it relates to is the amount of improvement that you can get with patching therapy, and that decreases dramatically as you get older.
Thank you. And going to the last question, any advice for future students who will delve deeper into neuroscience?
Oh, that's a wonderful question. So I guess you follow your own curiosity. If you're a student, you can explore a lot of thoughts, and through reading the right kinds of books. I found this field after reading a book, for example. I got really fascinated in how the brain represents images. If you want to look for, so that will give you lots of interesting ideas. Reading books will give you lots of ideas. And the other thing to do is talk to people. Okay, I find reading book at home is an enjoyment, but talking to people can open up opportunities and ideas that you never thought of before. I think talking to people, talking to teachers, professors, people who are doing work that you're fascinated by, talk to them after lectures, email them, track them down, and get this link to the research, because research is something that people do. So if you have an interesting question, people who are already doing neuroscience would love to talk to you.
The last question, sorry. What will affect the development of binocular vision of babies that was just born for several months?
Yeah. So what will affect the development of binocular vision of babies that has just been born for several months? So the things that the way that babies see the world is they typically see the world in a kind of typified way. So if their binocular visual system is giving them, say, healthy food, like everything is aligned, the systematic differences in the world are match up in the brain, then this itself is entraining the brain to set up the neural circuits that it needs for binocular vision. So it means basically experience affects the development of binocular vision, whether this experience is the normal kind of experience, or if it's the abnormal kind of experience, it will affect the development of the binocular vision. So that's what we term the sensitive period, is that period during which experience makes a huge impact on the way that the organism functions for the rest of its life. So yeah.
Next question. How could you measure how precise of human binocular vision, and how do you measure it? The precision.
Yes, that's fantastic. So in terms of stereopsis, what we do is basically we present things on a instrument like a stereoscope, and we use random dot stereogram. We isolate the cue, and then we just vary the amount of difference that we have between stimuli that are presented to the left and right eye. So that's how we do it in the lab, and that is a rigorous way to do it in the lab. However, when you go to the eye doctor, they will not do that. What they would do, they have panels, like pictures that are for red-green glasses, and they usually are combining stereo cues with object cues, so monocular depth cues, and they would ask you if you can see depth or not. So there's many different ways of measuring the precision of binocular vision in humans, and researchers in that field will say your threshold depends on the test that you used. As they always do. Yeah.
I think we have no more questions from the audience. And I have one curiosity, one question that might not relate to your topic. Are there possibilities to know the vision of extinguished animals or dead animals, such as dinosaurs? How will you say the scientists do?
Yes, I love that question.
Really?
That is a great question. I love it. So because I've always wondered about dinosaur vision. And so what people do in neuroscience, but also in zoology, is they look at indirect ways of inferring how animals saw, for example, that are long dead, like dinosaurs, or just deceased. So basically what you can do is, if you only have the skulls, which you do for dinosaurs, you can try to reconstruct the orbit of their eyes, and from that infer how they saw the world. So You can look at T-Rex, for example. You can look at where the holes are that kept the eyes and try to understand how they were moving, what kind of vision it had. That's one way. Another way is to look at the anatomy of the animal's visual brain and see how much of it is dedicated to visual input, right? So the tarsier that I showed at the beginning is very, very special because it's had a huge amount of brain only for visual processing. And we think that's because it needs vision critically to function at night, really good vision to see things at night, but also to jump on these insects that it eats from far away and know exactly where it is. So it has a huge brain that has specific features. So looking at the anatomy and how the cells are layered can tell you more about animals' vision. And of course, then we have behavior. When you observe the visual behavior of animals in the wild, you can see exactly how they respond to visual information. Yeah.
That is just so interesting. Thank you, Dr. Ip, for the very interesting and insightful talk and the very dynamic interaction with our audience today. There are a lot more to talk about, and we hope we can have more time to explore more on this topic.
Yeah, that's
due to
wonderful.
time constraint, we shall end today's session, and I hope we soon have another talk with you. When you come back to Taiwan, please visit, and I'm sure you will come back to NCU.
Thank you so much.
Thank you again for sharing with us today.
Yes. Thank you, everybody who joined. It was lovely to see you online.
Yeah.
Bye.